In my previous lecture, I defined the new physical quantity called work. Work is force times distance. There are three ways to calculate it, however, as we saw for our purposes here in Conceptual Physics AB. It depends upon whether or not the force vector points in the same direction as the displacement vector, is perpendicular to the displacement vector, or points in the opposite direction. At no time during that lecture, however, did I go through the importance of this new calculation of work. Why do we bother to define it? Okay, that's what we'll do here. We'll understand the reasons for defining work in the course of this lecture. It has to do with what is called energy. Energy is not a definition. Energy is recognized as a fundamental aspect to nature. So as I begin to describe energy to you, keep that in mind. Once again, this is not a definition. This is recognized as a fundamental property of nature. Okay, now with respect to energy, energy is usually described in the context of work. You may have heard this description of energy before. Energy is the ability to do work. Okay, now what does this description mean? Well, for example, I have here one of my air track carts, and let's say that I apply a force over a displacement to that cart like so. And in doing so, like we saw in the last lecture, I do work upon the object, and we can then, therefore, if we wanted to, calculate the amount of work done. However, what allows me to do work? What allows me to do work is this property that I must have that's just simply referred to as energy. Energy is the ability to do work. So if I can do work upon the object, then I must contain this property of energy. Now, when you watch this simple demonstration, you don't sit there and then say to yourself, oh, I see energy. In other words, energy is intangible. All that you see is work being done. So then therefore you can honestly ask the following question. Does energy truly exist? So once again, energy is intangible. In other words, you don't directly sense it. You don't see it, for example, when I do something as we did in this demonstration. Instead, you see work being done. So if work is being observed, therefore, truly, can we ask the question, does energy exist? Okay, now this was a question that was at the forefront of physics and in science in the early 19th century. So at this point in the course, by the way, we are well beyond Isaac Newton by a couple of centuries. Incidentally, in the early 19th century, what was happening in the United States, Western Europe, Australia, Canada, and a few other places scattered around the world? The beginnings of the Industrial Revolution. It wasn't a coincidence. The underlying science of the Industrial Revolution is understanding energy transfer. The Industrial Revolution was not possible without our understanding of energy. So then therefore in the early 19th century, this was a question that was being asked by the physics community at the time. So this is in the early 19th century. And this question coincides with the beginning of the Industrial Revolution. Okay, now the answer to this question is yes, but it's for a very specific reason. The reason is what's called the work energy theorem. Okay, now the word theorem implies that it's mathematical, and it is. I'll go through that description in a little while. But first of all, let me set up a simple qualitative scenario involving my air track here to describe to you what is meant by the work energy theorem just in words. So here's a qualitative description of the work energy theorem first. Okay, I'm going to do a little bit of erasing here. Okay, and now I'm going to set up the following demonstration involving the air track, and I will turn the air on to do this demonstration in just a few moments. Okay, so let's say that I have my air track like so. Okay, let's say that the air track is horizontal and frictionless. And then I have right here an object, my cart of mass m. We'll say that the cart is initially at rest. initial speed is equal to 0. And then let's say that I apply a net force horizontally to the cart. So like so is going to be a net force applied horizontally. I'm going to force the object in the same direction as the displacement vector. So then therefore I would do work very simply as force times distance like we saw in the last lecture. Okay, and then after I let go of the object, it'll end up over here with some speed v. So it's about as simple a scenario as you could possibly imagine. All that the scenario is as follows. Okay, so let me go ahead and turn on the air, like so. And then push the object. Like so. Okay, so when I just did this demonstration, I did net work upon the object. So if I do net work upon the object, force times distance, what allows me to do that work? Energy. So for example, let's just say, for the sake of argument, that I do 100 joules of net work upon the object. What that then means is that I used 100 joules of energy. If energy is the ability to do work, the amount of work that I do is then therefore equal to the amount of energy that I used. But this then brings us to a new question. If I used 100 joules of energy, what happened to that energy? So let me go ahead and write this out. So now let's say work is done, and then therefore energy is used. So then the next question is, what happened to that energy? Okay, now think about this question and then watch the demonstration again. For example, like so. So if I did 100 joules of work, I used 100 joules of energy, what happened to that 100 joules of energy? You may be saying to yourself that that energy was transferred to the object. You're correct. But how do we know that? How do we know that the object now contains 100 joules of energy? You may be saying to yourself, because the object is moving. That's not quite the correct way to think of it. Instead, think of the scenario in the following manner. I'm going to add something to the demonstration. What I'm going to add is a second cart, for example, like so. And now I'm going to go ahead and once again do work on this first cart. So here is the sequence of events once again so far. I do 100 joules of work on this first cart. In doing so, I transfer 100 joules of energy to that cart. But how do we know that this cart contains energy? Well, a moving object has the ability to do work on something else. In other words, this cart here had the ability to do work on the second cart. Therefore, this first cart must have contained energy. This is the simplest form that energy takes. It's the energy associated with motion, and it's called kinetic energy. A moving object must contain energy because a moving object can do work on something else. So now let's go ahead and add here to the description. The moving object now contains, as we say, kinetic energy. Kinetic energy is the energy associated with motion. It's the simplest form that energy takes. A moving object must contain energy because a moving object can do work on something else. So here is then essentially what the work energy theorem says. When net work is done on something, energy is transferred. The transferred energy becomes the kinetic energy of the moving object. The role of work, the reason why we define it, the role of work is to transfer energy. And even though we didn't go all through the descriptions of it, the mathematics of this specific type of multiplication called the dot product, it's a perfect representation of energy transfer. That's what the work energy theorem says in words. Let me write this out. So when work is done, energy is transferred. The transferred energy equals the object's kinetic energy. The role of work, once again, the reason why we bother to define it, the role of work is to transfer energy. Once again, this is what the work energy theorem says in words. Now, how do you say this mathematically while still keeping the situation as easy as possible? Actually, fairly easily. So let me now take you through the basic mathematics of the work energy theorem, and then I'll kind of generalize it to include more detailed scenarios. Okay, I'm going to do some erasing here. Make sure before I erase that you have everything written down, of course, in your notes. Okay, I'm going to use this same diagram here to describe the mathematics. Okay, so now mathematically. What we start off with is the definition of net work. This is why net work is so important, because it leads us to the work energy theorem. Okay, now net work. This is equal to force times distance, where I have the force vector in the same direction as the displacement vector. And now, here's what I have to do. What I have to do is turn this expression into a description involving the change in the object's motion from when it starts off at rest and ends up with some speed v. In other words, I'm trying to come up with a description of the energy associated with motion. I'm trying to come up with a description of kinetic energy. So how do I do that? Well, recall that net force from F equals ma, Newton's second law, is mass times acceleration. So now let's go ahead and replace the net force here with ma like so. And now let's go all the way back to one-dimensional kinematics. Okay, with one-dimensional kinematics for an object that started at rest, we saw the following two kinematics equations. First of all, the position equation. 1/2 at squared for an object that starts at rest. Now, back in our unit on kinematics, we originally saw this equation in terms of the displacement x. In this case, however, the notation is such that we write this as delta r. But this right here is the same expression as we saw in our unit on kinematics for one-dimensional motion with constant acceleration for an object that starts at rest. We also saw the following velocity equation as well, once again for an object that starts at rest. Like so. What I'm going to do is I'm going to algebraically combine these two equations together. What I'm going to do is take this expression here and solve it for the time t, plug it into here. And when I do, I'm then going to take that description of delta r and plug it here into the work energy theorem. Let's just see what happens when I run through these mathematical steps. Okay, now in order to do so, what I'm going to do first of all is take this expression here and solve it for the time t. So divide the acceleration to the other side of the expression, and the time t ends up being this expression here. And then what we'll do is we'll take that expression for the time t, and then we'll plug it into here. And when I do, I have to square each of the terms. So now the displacement delta r is equal to 1/2 times a, and then multiplied by t squared. So that's going to be v squared over a squared. Like so. And then notice that one of the A's will cancel here and here. If I now just kind of rewrite what I have left over, I have v squared over 2a left over. And now what I'll do is I'll take this expression for the displacement delta r, and I'll plug it in right here, just into the definition of net work. And then let's see what happens when I do. Okay, now I need to do some erasing, so let's go ahead and get rid of this, like so. And now net work is as follows. First of all, MA, and then multiplying by the displacement, v squared over 2a, like so. Notice that the a's cancel out, here and here, and if I just kind of rewrite what is left over, I then end up with the following term, 1/2 mv squared. This new expression, 1/2 mv squared, is interpreted as kinetic energy, the energy associated with motion. And kinetic energy is referred to as K. So to summarize the work energy theorem mathematically, as we're seeing it thus far, we can do so now in the following way. Let me do some erasing. Net work equals kinetic energy, K. In other words, when work is done, energy is transferred. The transferred energy then equals the kinetic energy of the object. This here mathematically describes perfectly what I've been saying in words throughout this lecture. Now, I've set up this derivation of the work energy theorem for a specific situation where the object was initially at rest. If the object was not initially at rest, if it was already moving with a speed of v0, for example, then the derivation involves a couple of extra steps. I'm not going to do those steps for us. Instead, I'm going to quote to you what those, or what the result rather, of those steps is. So if the object was initially moving with speed v0, then the work energy theorem is as follows. Net work equals the change in the object's kinetic energy. Once again, in order to derive this expression, it involves a couple of extra mathematical steps, which are not important for our purposes here. But if the object was already moving prior to me pushing it, it already had some initial kinetic energy. And then I do work on the object, and in doing so, I transfer energy to the object. I increase its value of kinetic energy from this value here to this value. The difference between the two, the change in the object's kinetic energy, that's equal to the energy that I transferred to the object by doing work on it. Net work is equal to change in kinetic energy. What we'll do next with our next example is we'll use this expression right here as our starting point. When we use this expression as our starting point in analyzing the next two examples, actually, we'll get a far deeper understanding as to what these examples are telling us in terms of energy transfer. I'll do those examples in the next lecture.